Hello everyone, this is Jason Kendall and welcome to the next of my introductory astronomy lectures. This time we're getting into the corpses of stars and what happens after everything has dead and gone and the stars have either exploded, gone into white, puffed off their outer layers as a planetary nebula. What is left from all those stars? We're going to begin with the low mass stuff, meaning white dwarfs. So we got two little videos coming up. The first is just on white dwarfs. The next one will be about novae and the type of supernova that happens with white dwarfs. So let's look at what a white dwarf is. Well, first we're going to look at this odd set of stars that are known in the HR diagram. We talked about this a long time ago in a previous lecture about what these are, but we never really discussed them very much. So there are some odd type stars way down in the lower left of the HR diagram, which tend to be very hot and extremely small. Their luminosities are very, very, very low, but their temperatures are high. Now, if their temperatures are high, because remember the temperature goes as the fourth power, and then if you multiply it, but if the luminosity's got to be low, then the radius has to be very small, or that R sub star. So what we have is the T sub star, which is the surface temperature of the star, R sub star, which is the radius of the star, and L sub star, which is the luminosity of the star. So if we multiply the surface area of the star, 4 pi r squared, times sigma t to the fourth, which is how much energy is being emitted per square meter on the surface of the star, we get the luminosity. If it's a really, really, really small star, then it can be really hot, and that'll make it underluminous, and those are the white dwarfs. And we have two fiducial ones. One of them is Procyon B, and the other one's Sirius B. And Sirius B is a late O-type in its spectrum, and Procyon B is an early A-type star in its spectrum, but they're different in their spectra slightly. In any event, they're the weird ones in the HR diagram, and they're small. So let's go back and then look at how we know about white dwarfs, and we're going to go back to our original talk about binary stars. So if you have two binary stars, a binary star, true binary star pair, are pairs that are bound together by gravity. And more than half of all the stars in the sky have some stellar companion, at least two, and some have more. And the brightest star in the sky, which is only about 7 light years away, is Sirius, or Canis Majoris Alpha, or just the dog star. And the dog star is the brightest star in the sky. It follows Orion in the winter skies, so that's why it's the dog. So Orion's the hunter, and the dog follows the hunter, of course. So that's why it's Sirius, the dog star. And it's actually a binary star. And how we know that it's a binary star was back in 1844, the German astronomer Friedrich Bessel looked at the proper motion of Sirius. Remember, proper motion shows the motion of the star across the sky with respect to the background stars, and it must have had some sort of unseen companion. And we can look at this particular set of graphs, and the big dot on these graphs is the motion of the bright star Sirius A, the star that we see across from with respect to the background stars. And he deduced that there must be a companion because that big star was wobbling in the sky as it moved. So there had to be something affecting its motion. In 1862, Alvin Graham Clark also then observed the faint companion, which he called the pup, which is very cute, because it's Sirius B. So Sirius B means the second star in a multi-stellar system. So if it's a double star, we always start with the primary star, we'll call it A, and the second star we will call B. And distinguish it from planetary systems, we use capital B instead. But the binary companion, the dim companion to Sirius in the sky, is called the pup, and it is Sirius B. So in 1915, the spectrum was observed of Sirius B by Walter Sidney Adams at Mount Wilson outside of Los Angeles, and he found that it was a faint white star. And so he thought, wow, this is a white star, means it's very, very hot. So the diameter was then determined back in 1959 to be very small, somewhere about the order of about the radius of the Earth. And in 2005, the Hubble Space Telescope team, a team using the Hubble Space Telescope, determined that it is nearly the diameter of the Earth, about 12,000 kilometers, and the mass of it is just a little bit bigger than the Sun. So something about the size of the Earth has the mass of just a little bit more than our entire Sun. And remember, in terms of physical size, the Earth is about 100 Earths fit across the Sun. So it had to have been, whatever this thing that's that massive, had to be compressed down into something very, very, very small. So what do we mean by that motion, and how do we know this thing has that mass? And the first thing we remember is what we call a balance. We can think of it as a balance of forces between two things around a fulcrum point, and if they're in orbit around each other, they're going to orbit a common center of mass. So if something's got a low mass and it's far away, then it'll move fast. And in order to say the big mass, which is close to the center of mass, moves slowly, but they move at the same angular rate, meaning they seem to have a rigid stick between them, and that they don't really have a rigid stick between them, but we're using the teeter-totter as an example. So imagine now that this isn't just a teeter-totter, it goes all the way around. So these three people get a really fun ride, because now take the ground underneath from them, and they can spin round and round and round. And the people that are the two women on the right who are close in, they're not going to get too sick because they're close in, so they won't be moving as fast. But the guy way out at the edge, he's going to be moving very, very fast. And that's because the mass of the two that are close to the center is larger than the mass of the one way out to the edge. And so this balances them. So the mass of one must be balanced by the mass of the other, must be the distance. So the only way for them to balance like this is if that's the center of mass, or the center of balance, which is the fulcrum of the teeter-totter. So that's what we're explaining here, is that we have two mass stars, M1 and M2, and the little m star is low mass, and the big M star, M2, is higher mass. And so the fulcrum point is shown by the triangle where the center of mass is. And so if you put a stick between these two stars, it would balance right at that point, and we would determine that balance point in the following way. We'd say their average distance between them is A, and the sum of the distances between each of the center of mass, which is the triangle, to each of the centers of the stars is A1 and A2. And so if you add those two up, you get A, which is the average distance. And that average distance is what we used way back in Kepler's laws in order to determine the average distance between, say, the sun and the planet. But now that we're not saying a planet, we're saying two objects that are of similar mass, as opposed to, say, a satellite orbiting Earth or a planet orbiting the sun. We're saying two stars, so they're almost in balance. So the center of mass is outside of both stars. And in so doing, we find that the ratio of the masses, M1 to M2, where M1 is the little mass, compared to the distances between them, A2 and A1, are reciprocated. So you'll notice that if the M1 is smaller mass than M2, then it will be farther away than A2. So the smaller M1 is, the farther A1 must be for the lever arm to work. So we combine these two definitions of the speed that we saw in the previous slide with the distance ratio and the mass ratio to balance them, and then we plug them into Newton's version of Kepler's third law, which we have at the bottom, where we have p squared equals 4 pi squared, which is just some number, divided by g, which is Newton's gravitational constant, times the sum of the masses, and all of that ratio is multiplied by the average distance, a cubed. So if it's just a solar mass and p is measured in years and a is measured in AU, then you reduce all the way down to Kepler's law that he derived in 1610. However, we're looking at Newton's version, where the masses can be of equal or roughly of equal size, or at least any size, or a comparable size. And the periods don't have to be measured in years, maybe they're measured in days, and the average distance might be measured in like tenths of AU or something like that. But really, we're going to measure the period in seconds, the masses in kilograms, and the A not in astronomical units, but rather in meters, so that G can have, the big G at the bottom, can have normal units associated with it. In any event, this is how we measure the masses of the objects, is by determining the period of the orbit and then determining the distance between them. So if we can determine their distances between them and determine how long it takes to do that, then we can determine the masses. And that can be done by looking at their actual orbits as they go across the sky. And as we saw before, there is a motion across the sky in proper motion. That when you take that motion across the sky and reduce it to the motion that they have orbiting each other, meaning let's just follow them across the sky, and instead of just saying, hey, look, they're going across the sky, look at their center of mass and see how they're orbiting their center of mass, and you get the two ellipses on the right. And where the graph meets in the center, that's the center of mass. So when they're far from the center, they're either far from the center of mass or they're as close they can be to the center of mass. And so they orbit as the dots, as you see in the arrows going around in the direction that you see. And every time there's a step of one dot, each of them goes a dot together. So when they're far from the center of mass, they go slowly, and when they're near to the center of mass, they go quickly, just as we expect from Kepler's law. So that means that Sirius B does a big loop, and Sirius A, the main bright star that you see in the sky, does a small loop. And that's what it means to have the braided motion that you see on the right, because the bright dot does a little motion across the sky, but the very difficult to see Sirius B star, which is very dim, does a big motion across the sky. And so we can actually reduce the proper motion to an actual distance motion by looking at how far apart they are. Now this data that we see here shows the actual position data sent relative to the bright star Sirius, which is now a dot, because now instead of saying, oh, let's look at the two ellipses, just center on the bright star Sirius and let's see how the other star, Sirius B, orbits it with time. And this is all the historical data that exists from 1862 to 2016, and this was compiled by Bond and his group in an Astrophysical Journal article in March of 31st in 2017. So this is pretty recent construction. And we see that there's photographic data, which is the blue data, lots of visual data as people have been doing things over 100 years. There's CCD imagery, as well as then the red imaging is Hubble Space Telescope imaging. And you can see that the Hubble Space Telescope provides some of the finest images along the line that really show exactly where it is in the sky. And this gives us an orbital set of parameters so we can actually see it. Now it's interesting that you don't see many data points when Sirius B is over on one side. And that's probably because, at some points in the year, well, Sirius is hard to view because the sun is in the same direction as Sirius. So it's very hard to get that data when it's over there on that side because the Sirius is up during the day. And so it's very hard to get that data. All right. So this is the orbital motion of Sirius B around Sirius A, which gives you the average motion, which gives you the period of the motion, how long it takes, and allows you to plug this into Newton's version of Kepler's third law in order to get the masses, or the sum of the masses. And if you know their relative distances, which we do because we can translate this angular distance that we see in the sky to an actual physical distance, because Sirius is so very close, it's only about 7 light years, that getting the physical size of this ellipse is actually pretty easy. So we use the physical size, we use the parallax of Sirius to get the physical distance. That allows us to know what the angular size that we see in this graph. Notice it says right ascension and declination, which gives you an angular size of that ellipse. And that angular size then can be translated into a physical size. Once you get a physical size, that is the A in Newton's version of Kepler's third law. And you can derive the period of the orbit from this kind of thing, and that gives you how long the period is. So you've got P for the period, A from the average distance between the two stars, and then that gives you, it allows you to derive the sum of the masses. And since we know their balance point, or their center of mass from the previous slide and the previous measurement, we then can derive the ratio of the masses. So now we have the ratio of the masses and the sum of the masses, which allows you to derive both of their masses. 2 equations, 2 unknowns, gives you a solution for both. That's how we know the mass of Sirius A and Sirius B. So that's called a dynamic value. And that allows us to get some interesting statements. And so here's the Hubble Space Telescope image from that time, and this was taken by Bond et al. For part of the study. And so that's obviously Bond's group has been part of has been studying this bright star because, white dwarfs are pretty cool. And this is Sirius B is this tiny dot, and there it is, and we see Sirius A in the background, which is overwhelming the light of Sirius B. But the statistics on Sirius B are interesting. It's a little bit bigger than the mass of the sun, meaning the mass is greater, but the radius is much, much, much smaller. It's less than 1% of the radius of the sun, or it's 0.8% or 84% of 0.84 of 1% of the radius of the sun, which means that's about 5,500 kilometers, which is about the size of the Earth. And the luminosity is very tiny, only 5.6% that of the sun. But the surface temperature is enormously hot, over 25,000 Kelvin, which is 4 times the temperature of the sun. So it's very, very hot. The average density, therefore, if we take the mass, and divide it by the radius cubed, 4/3 pi r cubed, we get an incredibly high density of 3 billion kilograms per cubic meter. That's a lot. 3 billion kilograms per cubic meter. And we also can derive an age from Sirius B. It's only about 228 million years old, which means this whole star has lived its entire life in the time frame that it took the dinosaurs to become born as dinosaurs 250 million years ago, until they died out, and then we were born. So basically this star was born at basically the same time the dinosaurs were born on Earth, or at least arose on Earth. The progenitor mass of Sirius B was about 5 solar masses, so we know that in the process of losing mass, it lost 4 solar masses, or a good 80% of the mass of the star was lost in the evolution of the star. So about 4 solar masses of the material was lost to space as a planetary nebula, and the progenitor type star was probably a B-type star. So another way that Sirius B's mass could be measured, and this is what Joyce et al. Did in 2018, is, well, actually this is extremely recent, from September 4th of 2018. This is like right now. This is data that just came out in monthly notices of the Royal Astronomical Society, or MINRAS, and the monthly notice said that they discovered that the diameter was about 7,500 miles, or 12,000 kilometers. And what's fascinating is the gravitational field for something that massive would be about 350,000 times that of on Earth. So if you weigh 150 pounds right now on Earth, you would weigh 50 million pounds if you stood on the surface of Sirius B. And therefore, a teaspoon of this white dwarf material would weigh, just a teaspoon, wouldn't weigh a pinch, wouldn't weigh a gram. Like a teaspoon of salt is a couple of grams. No, a teaspoon of white dwarf would weigh 5 tons, which is about the same mass as 2.5 or 3 SUVs, which is crazy, or 2 Humvees. That's really very heavy. The light, therefore, from the surface has to climb out of a very strong gravitational field, and in so doing, loses energy and gets stretched to longer wavelengths. And this is predicted by Einstein's theory of general relativity, and it's called gravitational redshift. And that happens around massive, dense objects. So they warp space-time around them, and as so doing, they change the wavelength. And so what we can do is look for specific wavelengths of light, specifically hydrogen, because there is a thin, thin, thin atmosphere of hydrogen. I mean, really thin atmosphere of hydrogen, less than a few hundred meters thick at the surface of Sirius B. And we know that since it's extremely hot, it should emit in that characteristic frequency of H alpha. Now it's currently like an OB type star, so we do expect those kind of spectral lines. And so we look for the shift away from them. And so we have the equation down the bottom that shows what we're hunting for. And lambda sub infinity means what did we on Earth observe the wavelength of light to be. And it's important to view this from the Hubble Space Telescope, because you get a gravitational redshift very gently as the photon descends into the Earth's gravitational field. But you don't get that from Hubble Space Telescope as much, because you don't descend as far to the surface of the Earth. So lambda sub infinity is the wavelength that we observe, and lambda sub e on the bottom is the emitted wavelength of light. So we're going to get the ratio of the emitted wavelengths. We know what the emitted wavelengths of light, because we understand what hydrogen does. And so then you say, well, okay, we know what we see it to be, we know what it was emitted at, and then we can determine the radius of the object. because the radius and the mass. So the ratio of the mass and the radius is that gm 2gm over c squared r. And if we have some proper way of measuring the size of the object, then we can get the mass. And so basically they were able to derive a mass measurement knowing the size of it. So the sizes can be the size can be determined basically from saying this is the Schwarzschild radius and how comparing it to the Schwarzschild radius, and that's what we get. So you can measure the mass of the object knowing its physical size by some hook or crook, meaning you have some radius measurement from, say, imaging, and then you determine by determining the spectrum of it, you can determine the wavelength that you observe it at, and you know the wavelength it was emitted at, and it allows you to determine the mass of the object. So this is how we know that the mass of Sirius B has 1.02 masses of the Sun by looking at the gravitational redshift of the light coming out of it. And I provided the two links there. That archive.org paper shows you exactly how they did this, and this paper came out on September 4th of 2018, which is really interesting. So there's ways you can derive the mass from the proper motion by looking at the motion of the two stars across the sky, and then there's a way of looking at the mass by measuring the size, by getting a size estimate, and then looking at the gravitational redshift. Then that'll give you the mass. And what's funny is they agree perfectly. So this is interesting to get two different ways of measuring things, and they agree. All right, so therefore we know the density is enormous because the mass is 2 times 10 to the 30 kilograms. The radius is about 5.5 million meters, and that gives a density of about 3 billion kilograms per cubic meter, or approximately 3,000 tons per sugar cube, which is huge. That's a huge amount of mass. So that's a thing, that is a huge, huge, huge density for objects for such a tiny object. And this is how big they are with respect to the Earth. This is a nice artist impression of how big a white dwarf is compared to the Earth. And if a white dwarf happened to pass this close to the Earth, or the Earth happened to pass this close to a white dwarf, well, that would be the end of the Earth. Because remember, a white dwarf has the mass of the Sun, so there would be enormous tidal forces across the Earth, and the Earth would be shredded by this. So this would be a way to die. And that's another funny name for this course is A Million Ways to Die. And a white dwarf passing right next to the Earth, a rogue white dwarf coming into the solar system, that would disrupt everything. Something the mass of the Sun passing through would basically tear the entire solar system apart, or at least send things flinging outwards and about. Even Jupiter would get flung out. Saturn would be flung out. The Earth would be torn to shreds if it got this close. Wow, what drama, and nothing could be done. Nobody could fly a spaceship and kick it out of the way. Oh, so sad. That's movie making 101. All right, so stellar graveyard. It's one of the many things that stars can end up with when they die. And a white dwarf is the core of a cold, dead star. And so as a star collapses, there's always this pressure, because remember, the whole thing, why stars do what they do is because gravity keeps pulling them in. And so some form of energy must be created or released in order to provide heat that provides pressure. And the pressure then resists gravity until there's something that either gets everything off of the thing in some great explosion like a supernova, or a planetary nebula pushes everything out in great thermal pulses so the weight's lifted, or the weight is never lifted and gravity keeps pushing and pushing and pushing until things get hotter and hotter and denser. Now, things collapse until there's new forms of pressure that take hold and allow a new form of hydrostatic equilibrium. But if it's too massive, then there's nothing that can hold it up, and it becomes a black hole, and we'll talk about black holes later. And all of these things are seen in the remnants of stellar evolution. So there's again the size of a white dwarf compared to the Earth, and interestingly enough, the escape speed, how fast you have to go from the surface of a white dwarf in order to escape. That's about 2% the speed of light. So in order to get off the surface of Sirius B, if you were standing there and then come home, let's say you took an Intrepid rocket and you landed on the surface of Sirius B, and somehow you survive the incredible heat and the incredible density and the incredible weight of your 50 million ton body, then that'd be tough. That'd be a really tough day, you know. But imagine you did that. But then you'd have to go 2% the speed of light just to lift off from the surface of that thing. That's really kind of fast. Not a lot of things have that kind of energy. So that, in fact, would be very difficult to make a rocket that could go 2% the speed of light. Nothing that's ever been built has, so that can't be done. And a white dwarf itself is a very, very strange object, and it has a degenerate matter core made of helium and carbon, and then a normal gas on top of it. Degenerate gas, normal gas, what do we mean? The normal gas is about 50 kilometers thick, or at the most, and basically once a white dwarf has been formed, they just cool off and become, after 10 or so trillion years, they finally emit all of their light and cool off to become a black dwarf. Now, the universe is only 13.7 billion years old, so no white dwarfs that have ever formed will have ever become black dwarfs. That will only happen in the deep, 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 deep future, long after the sun has died, long after the entire Milky Way galaxy has used up all of the gas and dust in it to make stars, long after all the other stars in the cosmos have gone out, and the only thing that's left are white dwarfs and neutron stars and black holes. That's what will be left, and these things will be spinning and emitting their heat for trillions of years and eventually cool to blackness. All right, so what do we mean by hydrostatic equilibrium? We're going to get into how white dwarfs hold themselves up against this enormous, enormous, enormous gravity and density. Well, remember that there's 2 points to this. At every layer in the star, and that's what that black dot thing means in there, is that at every radial point, every layer in the star, there's a balance between the gravity that's pushing it in from all sides and the gas pressure that's pushing it out from the center. And so something's got to provide the energy to give the pressure. Because remember, the star is leaking energy in the form of light. Because we actually see the star, we see the white dwarf, so it's cooling off. And the pressure there, and gravity doesn't cool off. Gravity always works to pull things together. So the gas pressure has to be provided by something, because that's the thing that's resisting the gravity. And as it cools off, the pressure reduces. So pressure and gravity oppose each other, and the gravity pulls it together, the pressure supports it, and when they're in balance, we call that hydrostatic equilibrium. Now, a white dwarf isn't actually collapsing. So how does it stay aloft at those incredible densities? But first, let's go back. Before we get to that, let's talk about what we mean by normal gases. So throughout the sun, even in the core of the sun, the ideal gas law, which relates the pressure and the temperature and how much stuff is in there and the volume, is how gases behave in the center of the sun. And that's pretty low density, low density. Remember we were talking about in the sun, the core of the sun could be as more dense than gold or lead by thousands of times. That's still considered low density for stars. That doesn't sound like low density for normal things to have something 1,000 times more dense than lead, but it is. So low density, and we're going to say, let's imagine that it's particles. Let's just say we only have electrons. Let's pretend we only have electrons. Well, we of course have helium nuclei and hydrogen nuclei and all sorts of stuff in there. Mostly that, but it's like helium nuclei, hydrogen nuclei, and electrons are dominantly what's in the sun's core. And so when you compress them, they heat up. And so this gas law, which relates to pressure, volume, total number of particles, and the temperature T, and temperature T is related to the energy by that K number, which is Boltzmann's constant. And in the ideal gas law, these things don't actually stick together. They don't have any interaction except bouncing off each other. So the hydrogen nuclei, the helium nuclei, and the electrons just simply bounce against each other with energy in the same way that billiard balls on the surface of a table, or people playing any kind of ball game where the ball bounces against something or against other balls, how the balls stay like balls. They don't distort or go anything. Well, of course, if you look really close, a baseball does distort. But when we look at particles like electrons and protons, they don't distort. So they actually behave like really rigid billiard balls. And so that's why you get that nice little crack sound, because the balls actually just impact and the sonic, and there's some sound dissipation as they impact each other, which is a very complex process actually. But in any event, the particles simply bounce off each other and exchange energy in their bouncing. And that bouncing is what we call temperature, because they run into each other. Some are running fast, some are running slow, but on average, they have an average motion, and that average motion we call temperature, which then relates to the total number of particles, n, and the pressure, which is how big it is, and the volume in which they are operating, or the box in which they are. An alternate version of the ideal gas law, which is the same as previous, but a little different. So you have brackets around the P, which means an average pressure instead of pressure at a particular point and for a particular size of volume. We're going to average the pressure over a much, much larger area. That's what those brackets indicate. And now we have it in terms of the density. And rho, which kind of looks like a weird looking P, that is the average density, meaning number of particles inside or mass, the average mass of a particle divided by the volume inside of there. But we want numbers of particles, where in the previous equation had an n, so we have the average mass is what we divide that average density by, and then we still retain the kT. So notice that the ideal gas law basically says it's equal to pressure times the density times the temperature. Well, divided by the average mass. So the average mass is composed of, say, hydrogen nuclei or helium nuclei, or you just take the average mass of those objects. And that's what we really mean. So we've got the average mass of the thing, the average density, and then we've got the pressure. But here we have three things: pressure, density, and temperature are the main things that go into this. And that's what comprises normal gases. Normal gases such as the air you breathe, the air that's in a combustion engine of a car, the gas that's at the center of the sun, and the gas that's at the top of the Earth's atmosphere, and even the gas, well, to some extent, well, the gases that are in Jupiter's atmosphere, and so on. So pretty much any normal gas that you will find, anything in a gaseous state on Earth, uses the ideal gas law to show how pressure, density, and temperature relate. However, in a white dwarf, all bets are off. We have a new type of gas law called the Degenerate Gas Law. So at high density, this new gas law takes over, because now we pack things in. We've said this is a very high density thing. So you pack everything into a really small volume. Everything is at these what we call low energy states, and only the high energy states are left, which is, what do you mean by that? And the result is what we call a degenerate gas. And the pressure then becomes independent of temperature, which is really weird. And so if you press on a degenerate gas, it doesn't get hotter, it just gets denser, which is weird. So if we press on an ideal gas, it can get hotter and not denser. It can say, I'm pressing on you. That means pressure gives it more temperature, and the temperature means average motion, which can keep the volume the same. But if you press on a degenerate gas, it gets smaller, because there's no temperature change, so the density goes up. Fascinating. All right, so to understand degenerate gases, now we have to understand them really detailed, so we're going to get into some serious details here. And we're talking about what's called the quantum regime of gases. And this is when the electrons, specifically electrons and protons, get packed so tightly together that, remember we talked way back in the de Broglie wavelength, we said that the wavelength of an electron is what it has when it orbits the nucleus when an electron orbits a hydrogen atom. And the total number of waves in the orbit determines the distance that the electron is from the center. So an electron can be thought of, and in fact it is correct to think of it, as having a wave-like property. So if the distance between separate electrons is on the order or very close to the size of their wavelengths, then we have to worry about quantum effects. And that's what happens at the densities of a white dwarf star. So a couple of things come into play, and the first is called the Heisenberg uncertainty principle, which says that you can't, if you really know the position of something, you can't know where it's going to be next. Or equivalently, if you know how much energy an electron has, then if you really, really are accurate about how well you know the energy, you will never know when exactly it had that energy, which is kind of a weird way of saying it. Or if you know exactly when it had the energy, you don't know what that energy is now. And that's what this equation at the bottom expresses. It says the product of delta x, which is where it is, times delta p, which is its momentum, or how fast is it moving times its mass, or where it's going to be next. The product of those two things must be bigger than some really tiny number. So this is actually that h bar over 2 is so small that it doesn't really matter in the large world. And it applies even in normal stuff, but that in normal size scales, but h bar is so small that we don't notice it. But in the quantum regime, when you're looking at things that are very high density and looking at very short time scales, then this really starts to matter. So delta x shows, let's say it's the characteristic size of an electron, or remember the de Broglie wavelength is said that the momentum is related to the wavelength. So in fact, they're the reciprocal. So what we have then is that the size of the object, delta, or you can even say where it's confined, the physical location it's confined. If you can really nail it down with, say, a pin, like a butterfly in a box, then you'll never know where to be next. Literally, you can pin it for the shortest period of time, but when you lift that pin up, or even you will have no idea where it's going to be after you measure where it is. That's what we mean by this. It's a very strange principle, the Heisenberg uncertainty principle. And second, we have what's called the Pauli exclusion principle. And this is the other thing that happens. No two electrons or no two particles can have the same energy, position, or state. And that's a very strange thought. What it means is that there's also another quantum mechanical concept called spin. And that's what we have with the 21 centimeter radiation that we're going to talk about extensively well, we already talked about that in looking for the cold gas in the Milky Way and looking at places where star formation exists. But when you have an electron can either spin up or spin down. And it can be either here or there with this momentum or that momentum. But no two identical electrons. And all of the electrons are exactly identical. So the only thing that separates an electron from another electron is where it is, what its momentum is, and what its spin is. And no two electrons can have the same quantum numbers of location, momentum, and spin. And when you get them really packed together, this becomes important. It doesn't really matter too much when they're far apart, but once you get down to white dwarf size, it's like, oh, you got that one, I got this one. So I'm keeping this, I'm going to keep, if you're here, but I got to have a different momentum just to be right on top of you. So you can have electrons on top of electrons so long as they have different momenta and different spins. Let's see what that works like. We're going to now consider what we call a one-dimensional example, where we're only going to use the left and right, which is delta x, confine it into a box going left and right. And we're going to look at the energy in form of momentum, which is p, going up and down. So the little squares are left and right position, meaning the delta x. And the delta p shows up and down for the energy. So really, we're kind of playing a little fast and loose with this, but just bear with me a bit. We can relate very easily the momentum to the energy. But you know, for those that are following along at home that really know what we're talking about, are going, wow, you're already violating some stuff. But basically, we're saying position and energy. Effectively, that's what we're saying. So what the little box says is that the electrons can either have a green arrow up, and that's spin up, or a green arrow down, spin down. They can be somewhere left and right, that's their position, or they can have energy, lowest energy at the bottom, highest energy at the top. All right, so that's so there are many, many, many boxes, and almost all of them fill the lowest energy states. Why? Because that's the lowest energy state, and most things have low energy, unless, of course, something comes along and gives them a kick. So when you pack things together, even in the gas like you breathe, if it had high energy, we would call that a high temperature, and it would be hot. And so things would be in upper levels, upper energy boxes. So when it's colder, everything goes to lower energy boxes. They don't change their positions, or they do because they're bouncing into each other all the time, but they don't go up because they don't get much energy because it's cold. So when we compress the boxes, let's say we compress it from left to right, or the right-hand side we're going to compress to the left. So there's 16 boxes going across. Let's say we compress it to the left. and we compress it down to 7 boxes. So some of these boxes will be filled at the bottom if we compress it very slowly and don't add heat. And that's called an adiabatic compression. And so we would allow it to be we'd compress this thing, and so that we could get more heat, things would stay in the low energy state, and then only the ones in higher energy states would be left. So as long as it can transfer heat around, then things will be in these low energy states, or high, they can be in both. But the point is there's lots of empty spaces for things to go to. Let's see how that works. So let's see how energy exchanges in a normal gas. So this is an example of a normal gas, meaning lots of open space, spins are roughly randomly oriented, most things are in the low state, and as you go upper and upper in the upper level states, there's fewer and fewer, but there's lots of space. And not everything's packed. You can see that you could pack them, but they're not. So let's look at one, and let's say 2 electrons approach each other. Remember, left and right means that's their separation physically. So as they approach each other, they get closer, and all of a sudden they're on top of each other. Remember, electrons have wavelength, so it's like this superimposition of 2 waves. And when they collide, it's like the 2 waves collide. And as they collide, they exchange energy, and one of them loses a little bit of energy to the other, and the other one gains a little bit of the other's energy, and then they move apart after the collision, and that means that they've exchanged energy. So the 2 electrons have exchanged energy, interacted, bounced off of each other, and they can do this freely and go across each other. But notice for a short period of time they occupied exactly the same space, but because they have a wavelength, because electrons have a wavelength, they had different energy, they could meet and keep going, but the momentum meant that they had to keep moving. And so when we average over the huge number of atoms that we typically, or electrons, that we typically have in a hot ionized gas, that this is what we call temperature, and that's what we call heat, is the average motion of all these electrons throughout as they interact and bump into each other. All right, so now let's see what happens when one bounces off what we might call a wall. So the wall might be the bottom, or the left-hand side we're going to call it a wall. And so we have an electron goes to a barrier, it goes and hits the wall. Now let's pretend that's actually the bottom. So maybe the electron hits the bottom of the box, or whatever it is, and there's nothing below it. In fact, that is the very core of the star. So it bounces off the core, loses energy because it's imparting that energy either to a wall, maybe it's just a normal wall because the gas in a room bounces off a wall and imparts energy, so that's why the air temperature, if it's hot in the room, the walls become warm too, because as the gas bounces against the wall, it imparts energy to the wall, and the gas that moves away from the wall. So you can see that the electron bounces on the wall, gives it the energy, and moves away from the wall. Left and right is movement left and right. Up and down is movement of energy. So eventually, these things collide and collide and collide and bounce off of each other, and if they interact with the walls and the walls don't steal the energy, then there's a total sum of energy and things eventually bounce into each other, and this would be like a little mishmash. And it might look, I mean, I can't do the animation because that would take me really long, but just think more that it's like the balls that you come up in like a Powerball sort of, or a lottery thing where the balls are popping up and popping up. That's much more like what we're talking about here. And these things would be moving and jumping and bouncing into each other, and some of the high energy ones would hit some of the lower energy ones and impart energy to them. But the total sum of all the heights and the total sum of all the heights that exist in here would be the total amount of energy in the system. So notice that you could sum up, okay, the ones on the far right, one of them has 2 energy points and the other one has 5 energy points. And you could say how high they are up from the bottom, where the bottom is 1 energy point. But since it's a ground state, we might want to say it's 0 energy. So we could call the bottom one 0, and the second row, or the second story on this graph, the 1 energy point. So that would give us the total amount of energy. And if it doesn't leave by leaking left and right into the walls, then these things would be bouncing into each other, and occasionally the ones in the bottom would go up high. And sometimes some of them would have all the energy go way up high, but they would lose that energy rapidly and drop back down. So on average, that total number of heights of all of the arrows from the bottom would be averaged over all of them, and not one of them wouldn't have all of it, but because that would mean that they keep bouncing into each other and losing the energy to that one, but that thing's going to be bouncing into others and imparting that energy. So when two came, they exchanged the energy. So you can exchange energy, and the total sum is constant inside the box. That's what we're talking about. So now let's compress it. Let's see what happens if we push it. So we're going to take a piston. So that red bar on the right-hand side is now a piston, and we're going to push on this box and make it smaller. And let's see what happens. First, the electrons try to push back on the piston by giving it energy to say, now you stay away, and they give the energy, and the piston says, okay, I'll stay away. But that imparts energy to the piston, warming the piston, but cooling the gas. And if the piston is relentless, it will push on the gas until it pushes them. But if the piston then pushes on it, it reduces the size, which then raises the temperature, just like a normal gas, like a PV-nRT. We've made the volume smaller, which has raised the pressure, which has given temperature, which has imparted more, given it more, push the ones in the lower boxes up, so that it actually forces energy into the system. Gives it more height in this diagram, if you will. And so the more we compress it, we give the electrons energy and they hop up. So we keep pushing on the piston, and it heats the gas by moving the electrons, which are these arrows, up into upper states. So now the electrons go up, and therefore they have more energy, so they're bouncing around. Of course, the graphic doesn't show that. It's too difficult for me to do all that, so I did not do it. So that gives them energy, and they're going to be bouncing all over the place. And as we can see, they can bounce off of each other and reduce that energy. They can also bounce into the wall and reduce down and impart the energy and try to keep the piston up. But notice what we also have here is that the electrons can pack into a box, so long as one of the boxes has spin down and one of the boxes has spin up. So long as you can't have two spin ups in one box, you can't have two spin downs in one box. And that means they can occupy the same exact space and have exactly the same energy, so long as they have different spins. And that's what we're going to start to do now. Let's really push on this thing. We're going to press with this piston relentlessly, never stop pushing, and compress this thing down to a really small space. Boom. Now, if you keep pushing and pushing and pushing and pushing, then all of a sudden, eventually, over time, and if the pushing eats the energy, then what's going to happen is all the electrons will be packed down into the smallest possible volume. They'll all have everything will lose all its energy. It'll be pushing against the piston, but notice it can't compress anymore. There's no place for it to go. It can't be pushed into. And basically, in order to actually push into it, the piston has to now impart energy. It has to give energy into the system instead of letting the energy redistribute, because that's what we did before. We let the energy redistribute. But now, in order to push this thing smaller, make it less than 6 boxes left and right, the piston has to say, I'm a hot piston, I'm going to push on you and go impart more energy. So let's get rid of the piston for a bit and pull all the way around and look at the side. The way we can now think about it is that we can say the whole box is being pushed at from the right by the self-gravitation of all of the electrons themselves. So now there's no piston. Let's pretend there's no piston. And what we have is that the electrons are packed together. The gravity from all of these things is so strong because they're really pulling on each other. So the self-gravitation is the piston. So the left-hand side of this box might be the center of the star. The right-hand side of this box might be the surface of the star. And so now we see that they've imparted all their energy to try to get rid of it. It's gotten rid of all this energy, but now the electrons are in these low states. They can't do anything. So to actually compress them, you have to give energy into the system in order to move the electrons out of the box and up in energy. So notice they're occupied the bottom 3 rows, and there would be more energy in order to go to the 4th row. And if it's gravity, just is like saying, I'm not going to do anything because I'm compressing you. So this is a stable state because now this is the self-gravitation of all of these electrons on each other, and they're in their lowest possible state. And this is what we mean by a degenerate gas. A degenerate gas is compressed maximally. All of the electrons in an electron degenerate gas, they all occupy the lowest possible energy states. They all occupy they all occupy both the lowest energy states, and they're compressed together such there's no physical space between them. And this acts like a brick wall that supports the self-gravity of each other because they can't go anywhere. You can't put 4 electrons in one box. You can't put 3 electrons in one box. You can only put 2, and 1 spin up and 1 spin down. That's the Pauli exclusion principle. And now the Heisenberg uncertainty principle says that you don't know what's going to be happening next to any one of these. Because notice that these things are here in these boxes, but because they're individual electrons, they can be jumping from point to point to point, and you can't tell. Because the one of them will become the other, and the other will become the one, and they'll actually be moving around inside of there, but they're all identical, so it's as though they're staying still. So if you push on it harder, then you have to impart energy. So if the only way to do that is if the self-gravitation somehow overcomes it, maybe there's too much mass, and the gravity gives a little bit more energy, it forces them out into the upper level. Now you've got this gas that's bouncing off of it. But the funny thing is that those top layer, notice if it bounced against the wall of the bottom or the wall of the top, they can't cool down. So now in the previous examples, we had the electron gas cooling down by bouncing against the wall and moving to a lower energy level, meaning down the stack. None of the ones that we just bumped up can't actually cool, so they stay hot. That's very strange. So we can think of them as in their lowest state. They're very, 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 very hot, and they can't cool down. There's no way for them to cool down because cooling down means going to a lower energy state. They can't do it. So as you compress a degenerate gas, you're forcing them to have more and more and more energy, which means and there's no way for them to lose this energy, so they stay energized. And the energy is provided by the pressure due to the self-gravitation of all the electrons pulling on each other. So all these green arrows have mass. And because they have all mass, they're all pulling on each other. And as they're pulling on each other, that's the self-gravitation of all these green arrows pulling on each other. All right, so that's what we mean by the self-gravitation. They pull together on each other. And this piston is unstoppable because it's gravity. It never ends. That they can never cool down. The only thing that could possibly happen is, what if we add more mass? Well, that adds more self-gravity. Maybe we add more layers on. That means that if you add more electrons to this box by dumping them on from, say, the right-hand side, let's say the left-hand side, the center of the star, the right-hand side is the surface. If you dump electrons on from the right, they have to land on it with high energy. If they land on it with high energy, they stay hot. There's no way for them to cool down. They become part of the degenerate electron gas. In a very real sense, we can think of this as like a big subway car. So start way uptown in New York City. You start on the end of the A line with nobody in it, and a couple people sit on the lowest, get seats. And so you get to a few stops down, every seat's full, and so everybody's seated. And now the next stop, after everybody's seated, people get on and they're standing room. And so that's the second level, is standing room. Eventually you get long enough that there's the standing room's filled. And let's say it's an extraordinarily busy day, and people still keep packing in. Well, where are you going to go if all the seats are taken and everybody's already standing? Well, you get on top of people's shoulders. That's the third level. And so now we're up on top of people's shoulders. And people are getting really irritated with that because people are on top of your shoulders, so they're going to shove you around. So the people that are on top of people's shoulders get shoved around, and so they never stop moving. That's the third level. Well, we keep going down the subway line. Now we get to Times Square. Now we've got people seated who aren't getting off. People standing who say, I'm not going to give up my standing spot until I get a seat. And the people who are being shoved around above on top of those people, like at some crazy concert, they try to get on. That's the fourth level. And they have to get on top of the people who are being shoved around. So everybody's annoyed. So a degenerate gas is a whole bunch of people in a subway car that can't leave the subway car. The subway car is not getting any bigger, and everybody's just getting more energy as you keep packing stuff in. Here, energy equals anger or heat, because they broke the air conditioning too, just to make it fun. So you can't cool off, you can't get off, and you can't leave, and you can't sit down, and you can't stand. That's the electrons in a degenerate gas in a white dwarf. All right, so what does that mean? White dwarfs cannot cool, so therefore the pressure is not dependent on the temperature, it's only dependent on the density. So remember we had from before the ideal gas showed pressure equals some density times some temperature. Well, now we are different. We have pressure equals some constant number times the density to the 5/3 power. That's kind of weird, but look at the constant. I just said pressure equals some constant. Look at the constant below. Don't worry about that. That's just what you'll find if you go hunt around on Wikipedia. It's based off of the mass of the electron, the mass of the proton, and Z over A is equal to the total number of particles compared to the atomic number to 5/3 power. And there's a pi and an H, which tells you it's a quantum effect. But basically, the pressure is to the density to 5/3 power. The funny thing is that if you looked at the temperature, if you took the energy that's imbued inside a degenerate gas and spread it out, it would be though that the electrons have a temperature of billions of degrees because they're occupying so much of the energy. Remember, the energy is how high the sum of all the boxes are off the ground with all the electrons. So really, there's a huge amount of energy inside of it. It just can't cool off. So it would be the equivalent of it being billions of degrees if they were free to move. But they can't move. They're being compressed by their self-gravity. So what does this mean for this? Let's kind of get an idea of where the density comes from. This is the central pressure of the core of the sun, and this comes from a previous lecture. So let's kind of go blazingly through this. The pressure at the core, P sub C star, sun, which is the circle with a dot in the middle, that's the pressure at the core of the sun, is basically the mass of the sun divided by the total mass of the sun divided by the total radius of the sun squared. That's roughly it, times the gravitational energy of the entire sun, which is G, m mass of the sun divided by the radius squared. So the pressure at the core of the sun roughly goes like the Newton's gravitational constant G times the mass of the sun squared divided by the radius of the sun to the 4th power. It's roughly where that comes from, and that comes from the stellar structure equations we see on the upper right. And giving that kind of thing, it tells us that the central pressure of the sun is something like 10 to the 16th pascals, or 100 million times what it is at the bottom of the Mariana Trench. And normal air pressure is about 10 to the 5th pascal, so that's pretty dense. What's funny is, even at that high pressure, when it's tens of millions of degrees, that's still a normal gas because the temperature is enough to keep it not degenerate. All right, but white dwarfs are smaller. Well, let's take that equation that we had for pressure, where pressure equals gm squared over r to the 4th, but instead of using the pressure due to an ideal gas, now we're going to use the pressure due to a degenerate gas. And that tells us an interesting thing. Pressure degenerate is rho to the 5/3 power, which is like the mass divided by the volume cubed, which is radius cubed. And that's what we mean. That's where that m to the 5/3 and r to the 5th power comes from on the right-hand side. So now we can equate those two things, which is the self-gravitational pressure, gm squared over r to the 4th, which is the pressure due to the entire star pressing on itself due to gravity, and we equate that roughly to the degeneracy gas pressure, which is m, the mass of the star to the 5/3 power divided by the radius to the 5th power, and solve the algebra, and we find that the radius of a white dwarf is proportional to the mass to the minus 1/3 power. That's very, very strange. The more massive a white dwarf is, the smaller the radius. That's what the thing in green circle says. So if you had a white dwarf with 10 solar masses, which doesn't exist, but let's pretend it is, and there's something, maybe a different white dwarf that's 1,000 times more massive than the previous white dwarf, then if you have something 1,000 times more massive, then it will be 10 times smaller. So one object, something 1,000 times more massive, will be 10 times smaller in radius. That's crazy, but that's what happens with the degenerate gas, and that's what happens with white dwarfs. So more massive they are, the smaller they are. So that doesn't last forever, because the mass, if it goes up and up and up, that would mean that the larger the mass, the radius gets tinier and tinier until you could imagine that the mass could become infinite. Imagine there's stuff that just never stops dumping on top of the white dwarf. It would get smaller and smaller and smaller until it became the size of a speck, or zero size, which is bizarre. So that can't happen. Why can't that happen? Because as the pressure goes up, it gives the electrons more energy. The energy then becomes like a speed, and speed means they're bouncing around really fast. The highest energy means that the speed means it's very close to the speed of light. So it can't go faster than the speed of light. So there must be a limit to the total amount of stuff you can pile onto a white dwarf, because if you give it too much energy and too much stuff, the density goes up. As the density goes up, the energy goes up. And eventually some of the electrons would have so much energy that they're almost going the speed of light. And once you get there, it's called a relativistic degenerate gas, and that's what we see at the bottom, which is basically PDG is a relativistic degenerate gas, and it's to the density of the 4/3 power. So it changes as it goes from a normal degenerate gas to a relativistic degenerate gas. And there's a different constant out front, but notice the mass of the electron has disappeared because it's really small, or at least it becomes, the reciprocal of the electron mass becomes very small as you get closer and closer and closer to the speed of light. Anyway, the relativistic degeneracy then blocks this thing and says there must be a maximum mass. So we can go back to to inform us of what to think about with the ideal gas law, and say if the pressure times the volume equals the self-gravitational pressure, which is what the green arrow is trying to indicate to us, we say the average pressure of a star and the average volume of a star is equal to the self-gravitational energy, which would be gm squared over the radius of the star, the mass of the star squared divided by the radius of the star squared. That minus 1/3 comes from the self-gravitational energy of the entire star on the top of itself. So we can think of the pressure times the volume equals the self-gravitational energy, and we can plug in the degenerate pressure and see what we get. So we then say, okay, fine, degenerate pressure times the volume is proportional to that 1/3 gm squared over r. We can get rid of that constant and muck around with it. We know the volume goes like the radius cubed, and we know the density goes the mass divided by the volume, and we get this really funny number at the end, because all we get is a mass, because we got a relationship between the mass. We can get rid of the volume as a radius, and the radius solves out. It actually drops out because we get a cube of the radius. And the radius disappears, and we find that there is an absolute maximum to the mass of a star when the relativistic degenerate gas becomes the entire self-gravitational total energy of self-gravitation. We find that the maximum mass for a white dwarf is 1.44 solar masses. That's really strange. That's what that latter equation says. It's called the Chandrasekhar limit. And the Chandrasekhar limit basically says that the maximum possible mass for a white dwarf is 1.44 solar masses. And Subramanian Chandrasekhar derived this from Fowler's work a few years prior, who basically found the previous stuff we were talking about, but did not do the relativistic calculation. Subramanian Chandrasekhar in July of 1930 was on board a steamship from India to Cambridge and derived the equation that we just saw above for the relativistic version, and derived the maximum solar mass on his way to go to studies. I think he was 22 or 25 years old when he did this. So above this mass, the electron degeneracy must fail, because then the electrons would have to be traveling at the speed of light. So that gives a prediction for the maximum mass, and that's upheld by observation. There is no white dwarf that's ever been observed that is more massive than 1.44 solar masses. And this is described in this little thing, the non-relativistic Fermi gas, which is the m to the minus 1/3. But if we add in the relativistic terms, meaning it can't go faster than the speed of light, because speed of light, you get the limit of the Chandrasekhar mass, which is 1.44 solar masses. So white dwarfs themselves are the remnant cores of dead stars. And they're stars which were formed from something about less than 8 times the mass of the sun. They're supported against the pressure of their enormous weight. Remember, a typical white dwarf is about as big as the Earth, by the electron degeneracy pressure, which is just basically pack the electrons together. And below about 4 solar masses, the principal components of a white dwarf are carbon and oxygen nuclei, and very little helium and hydrogen nuclei on the surface that compose a very, very tiny atmosphere above that. But between 4 and 8 solar masses, they're primarily oxygen, neon, and magnesium white dwarfs. And all of these things are less than 1.44 solar masses. The radius of them are about the size of the Earth, or about 2% that of the Sun. And the densities can be up to 1,000,000 grams per cubic centimeter. So that means you can get 1,000,000 grams of something that's the size of a sugar cube. And the escape speeds are on the order of about 2% the speed of light. Here's the funny thing. All this stuff we were talking about, there's no nuclear fusion anymore. This is the end state of a star. All the nuclear fusion is done. They're not gravitationally contracting either. So there's just residual heat. And where's that residual heat? It lies in the protons and nuclei, the helium nuclei, the carbon and oxygen nuclei, the neon and magnesium nuclei, because they're dodging around between the electrons, among the electrons that are supporting the star from its collapse. So the nuclei are still hot, and they're behaving like a normal gas. They are not degenerate. So they can cool. They're at this incredible temperatures of maybe tens of thousands or hundreds of thousands of degrees, and they behave like a normal hot gas. And they emit light because they're hot, and that's the light that we see from Sirius B, 7 light years away, is the light from the very hot nuclei. The electrons, they never can cool off. They'll never stop that degeneracy. They'll never break that strange brick-like structure of degeneracy. But the nuclei of carbon and oxygen and helium and hydrogen, the very tiny amounts of hydrogen on the surface, will get colder and colder, and that light is that's what we see as the light. And that's about the thing about white dwarfs. So next time we'll see how they blow up.